Okay, we're going to look at number 39. Number 39 says as a particle is located at each corner of an imaginary cube, so all sides are equal. Each edge of the cube is 0.25 meters long, and each particle has a mass of 0.12 kilograms. What is the moment of inertia of these particles with respect to an axis that lies along one edge of the cube? Okay, so we have our cube, and we have 8 different points, each on one side of the cube, so we have 8 particles, which also means that we have 8 different moments of inertia. So here we label them. So we have 8 different moments of inertia around this axis of rotation. So in order to find the total inertia, we need to find the moment of inertia for each and every one of these particles. Now I1 and I2 are easy because they actually lie on the actual axis of rotation. So remember, the moment of inertia is mr squared. So the r is 0, so it's just m times 0 squared is 0, so the moment of inertia for point 1 and point 2 are 0. 4.3. Now, the r that we're using for 4.3 is the perpendicular distance from the axis of rotation. So it's almost like the shortest distance to the axis of rotation. And the shortest distance from 3 to the axis of rotation is this line right here. So the inertia of that is the mass of the particle times 0.25, which is the length of the cube that they gave us squared, and they gave it 0.0625. For the fourth one, even though the fourth one's on the lower edge of the cube, the axis of rotation is still there between particles 1 and 2. So the distance, the perpendicular distance from the axis of rotation is still 0.25 meters. So I4 is still m times 0.25 squared. So again, the moment of inertia for particle 4 is also 0.0625. For particle 5, the shortest distance is the diagonal of the cube, which we will call L. We'll find L using the Pythagorean theorem. L is equal to a squared plus b squared, and L is the c squared, because the diagonal kind of breaks up the cube into a right triangle, with L being the hypotenuse. So we find L, and now we don't have to use the square root because 0.25 squared plus 0.25 squared equals L squared, and it's m times L squared, so we don't need to square root it and then square it again. So what we end up is 0.125 m is the moment of inertia of 5. For 6, it's pretty much the same thing. We have to find that diagonal, the shortest line to the axis of rotation. So we end up getting 0.25 m again for 0.6. For 0.7, the shortest distance, it's that length right there. So it's also going to be 0.0625 times the mass. And then the last point, 0.8. The shortest point to point 8 is that side right there, which is also 0.25 squared times m will give you the moment of inertia, which would once again get 0.0625. To find the total inertia, we have to add up all the inertia of these particles together, and we get 0.5 times the mass. Now I've been using m just so we don't write down so many numbers, but we know what the mass is. So the total inertia is 0.5 times 0.12 kilograms, which means that the total inertia, kind of ate the square there, the total inertia is 0.06 kilograms meters squared, and that is our answer for this problem.